Proper way to feed time series data to stateful LSTM? Let's suppose I have a sequence of integers 0, 1, 2, ... and want to predict the next integer given the last three integers, for example 0, 1, 2, 5, 3, 4, 5, 6, etc. Suppose I set up my model like so. It is my understanding that model has the following structure. Please excuse the crude drawing. First question, is my understanding correct? Note I have drawn the previous states, C_T1, H_T1, entering the picture as this is exposed when specifying stateful equals true. In this simple next integer prediction problem, the performance should improve by providing this extra information, as long as the previous state results from the previous three integers. This brings me to my main question. It seems the standard practice, for example see this blog post and the time series generator Keras preprocessing utility, is to feed a staggered set of inputs to the model during training. For example, this has me confused because it seems this requires the output of the first LSTM cell, corresponding to the first time step. See this figure. From the TensorFlow docs. Stateful, Boolean, default false. If true, the last state for each sample at index I in a batch will be used as initial state for the sample of index I in the following batch. It seems this internal state isn't available and all that is available is the final state. See this figure. So, if my understanding is correct, which it's clearly not, shouldn't we be feeding non-overlapped windows of samples to the model when using stateful equals true? For example,
the answer is, depends on problem at hand. For your case of one-step prediction, yes, you can, but you don't have to. But whether you do or not will significantly impact learning. Batch versus sample mechanism, see AI equals see additional info section. All models treat samples as independent examples. A batch of 32 samples is like feeding one sample at a time, 32 times, with differences, see AI. From model's perspective, data is split into the batch dimension, batch_shape 0, and the features dimensions, batch_shape 1 column, the two don't talk. The only relation between the two is via the gradient, see AI. Overlap versus no overlap batch. Perhaps the best approach to understand it is information-based. I'll begin with time series binary classification, then tie it to prediction. Suppose you have 10-minute EEG recordings, 240,000 time steps each. Task, seizure or non-seizure? As 240K is too much for an RNN to handle, we use CNN for dimensionality reduction. We have the option to use sliding windows, i.e. feed a subsegment at a time. Let's use 54K. Take 10 samples, shape, 240,000, 1. How to feed? (10, 54,000, 1, all samples included, slicing as, sample 0 column 54,000, sample 54,000 column 108,000, 10, 54,000, 1, all samples included, slicing as, sample 0 column 54,000, sample 1 column 54,001. Which of the two above do you take? If 2, your neural net will never confuse a seizure for a non-seizure for those 10 samples. But it'll also be clueless about any other sample. i.e., it will massively overfit, because the information it sees per iteration barely differs, 154,000 equals 0.0019%, so you're basically feeding it the same batch several times in a row. Now suppose, 3, 10, 54,000, 1, all samples included, slicing as, sample 0 column 54,000, sample 24,000 column 81,000. A lot more reasonable. Now our windows have a 50% overlap, rather than 99.998%. Prediction, overlap bad. If you are doing a one-step prediction, the information landscape is now changed. Chances are, your sequence length is far from 240,000, so overlaps of any kind don't suffer the same batch several times effect. Prediction fundamentally differs from classification in that, the labels, next time step, differ for every subsample you feed. Classification uses one for the entire sequence. This dramatically changes your loss function, and what is good practice for minimizing it. A predictor must be robust to its initial sample, especially for LSTM, so we train for every such start by sliding the sequence as you have shown. Since labels differ time step to time step, the loss function changes substantially time step to time step, so risks of overfitting are far less. What should I do? First, make sure you understand this entire post, as nothing here's really optional. Then, here's the key about overlap versus no overlap, per batch. One sample shifted, model learns to better predict one step ahead for each starting step, meaning, 1. LSTM's robust against initial cell state. 2. LSTM predicts well for any step ahead given X steps behind. Many samples, shifted in later batch, model less likely to memorize train set and overfit. Your goal, balance the two, one's main edge over two is. Two can handicap the model by making it forget seen samples. One allows model to extract better quality features by examining the sample over several starts and ends, labels, and averaging the gradient accordingly. Should I ever use 2 in prediction? If your sequence lengths are very long and you can afford to slide window W/tilde 50% its length, maybe, but depends on the nature of data, signals, e.g. Yes. Stocks, weather. Doubt it? Many-to-many prediction, more common to see, 2, in large per longer sequences. LSTM stateful, may actually be entirely useless for your problem. Stateful is used when LSTM can't process the entire sequence at once, so it's split up, or when different gradients are desired from backpropagation. With former, the idea is, LSTM considers former sequence in its assessment of latter. T0 equals sec 0 column 50, T1 equals sec 50 column 100, makes sense, T0 logically leads to T1. Sec 0 column 50, sec 1 column 51, makes no sense, T1 doesn't causally derive from T0. In other words, do not overlap in stateful in separate batches. Same batch is okay, as again, independence, no state between the samples. When to use stateful, when LSTM benefits from considering previous batch in its assessment of the next. This can include one-step predictions, but only if you can't feed the entire sec at once. Desired, 100 time steps. Can do, 50. So we set up, T0, T1, as in above's first bullet. Problem, not straightforward to implement programmatically. You'll need to find a way to feed to LSTM while not applying gradients, for example freezing weights or setting LR equals 0. When and how does LSTM pass states in stateful? When, only batch to batch, samples are entirely independent. How, in Keras, only batch sample to batch sample, stateful equals true requires you to specify batch underscore shape instead of input underscore shape, because, Keras builds batch underscore size separate states of the LSTM at compiling. Per above, you cannot do this. This implies 21 causally follows 10, and will wreck training. Instead do batch versus sample, additional info. A batch is a set of samples, 1 or greater, assume always ladder for this answer. 3 approaches to iterate over data: batch gradient descent, entire dataset at once, stochastic GD, 1 sample at a time, and mini batch GD, in between. In practice, however, we call the last SGD also and only distinguish versus BGD, assume it so for this answer. Differences. SGD never actually optimizes the train set's loss function, only its approximations. Every batch is a subset of the entire dataset, and the gradients computed only pertain to minimizing loss of that batch. The greater the batch size, the better its loss function resembles that of the train set. Above can extend to fitting batch versus sample. A sample is an approximation of the batch, or, a poor approximation of the dataset. First fitting 16 samples and then 16 more is not the same as fitting 32 at once, since weights are updated in between, so model outputs for the latter half will change. The main reason for picking SGD over BGD is not, in fact, computational limitations, but that it's superior, most of the time. Explained simply, a lot easier to overfit with BGD, and SGD converges to better solutions on test data by exploring a more diverse loss space. Bonus diagrams.